All right. Hello, students. This is going to be a very brief lecture to give you the tools and some resources to help you take on your case study assignment to design a rainwater harvesting system. Okay, and I should state for the record, I am your humble professor, Charles Newman, and this assignment is for Columbia University's Engineering for Community Development course in the Civil Engineering Department. So, what is this case study assignment? So essentially, this is going to be a back of the envelope calculation that we are asking from you. So I should say, do not submit an envelope with chicken scratch on it. No, all of this information, obviously it's through courseworks and you can submit your assignment through there. But what are we trying to achieve with this assignment? So I'm hoping to is for you to understand how to size a water catchment system first and foremost. But then what assumptions went into that process and how did you come to your conclusion? We're going to be talking a lot about assumptions this semester. And then finally, how might you determine the reliability of your system? So let's jump into the assignment and the prompt. A farmer in Kibwezi, Kenya has a rooftop of 100 square meters. And the farmer has a family of 6, including herself. Currently, they purchase water from a local kiosk that sells water piped from a nearby spring. And they want to install a rainwater harvesting system, and they have asked you for some guidance. So I'm going to break down a few questions here, and I'm asking you to answer each question in 1 to 3 sentences upon your submission. And I should also state for the record, we are going to assume that this water is not for agricultural use. Okay, this is only for household use. But that then brings up some questions. So how do you estimate for the family's daily water use in liters? How did you come to this conclusion? And how would you characterize the family's use of water? You're going to have to make a lot of assumptions here, but there are a lot of sources out there that can help give you some direction. Secondly, or perhaps principally, approximately how big of a storage tank would you recommend in liters or cubic meters? Either is fine. Does it meet all demand? And if not, what percent and what time scale is that based on? Okay, this question may make a bit more sense as you get into the calculations. And how did you come to your conclusion? Again, what assumptions did you make? And of course, what sources did you use? And then secondly, or lastly here, we're going to ask for some reflection. So how reliable would you say your tank will be? And if you were to undertake a more complex calculation, what additional considerations would you include? And then most importantly, what did you not consider in determining demand for the size of the tank? What do you think would be most important? What would you ask the family? You have no opportunity here to ask the family beyond what the prompt gives you. Okay, so these are a lot of questions, and you're probably scratching your head. Okay, well, where do I begin? Well, I will tell you a very good place to begin, and that is with local rainfall data. Here's the link. These slides will be available right next to this video, that's a good place to start. Okay, so we talked a lot about assumptions just now. What do I mean by assumptions? We haven't gotten too much into assumptions yet this semester. So what are some examples of assumptions? All right, so you're going to have to consider demand. As I mentioned, this is, we're not talking about agricultural use, but there's demand within the household that is potable water for sort of direct consumption, but there is also non-potable use. All right, there's dishwashing and laundry. Are you going to consider these factors as well? Supply, rainfall data. Are you going to develop your calculations based on monthly trends, or are you going to design to the driest month? Again, as you get into your calculations, this question might become a bit more understandable, right? And then our first flush system. These are cool little contraptions. I just threw it in here because I want to share them with you. I'll get into that in a moment. And then a roof coefficient. This is an essential constant that you will need to factor into your calculations. I'll get into that in a moment as well. Okay, and then sizing and selection. In this prompt, we are not sort of considering cost. All right, so cost benefit is not really considered, and cost in terms of time and money. So if your solution results in a very large water tank, I mean, presumably that's very expensive. Is that something that you might want to consider in adjusting your answer after showing all of your work with your calculations, right? We haven't been considering reliability or treatment in the prompt. So these are sort of example assumptions that will be important potentially to touch upon. Okay. So I've provided one resource which can direct you to local rainfall data, but it will be helpful to have some additional resources. So the UN Right to Water and Sanitation is a document. It's linked here, again, slides on Courseworks. This could provide some useful data that will help you sort of establish or decide upon your appropriate demand calculation. The Sphere Handbook is also a very useful resource for similar data. And then rainwater catchment systems for domestic supply. This is a handy little book. I don't know if you can see it, it's all blurred there. I have my own copy. This book is quite helpful in helping you understand all of the factors that are involved with the design of rainwater catchment systems. And as you'll see, it also presents a couple cool examples and solutions. Okay, so real quick rundown of the basic rainwater harvesting system components. First of all, we have our primary components, which is of course the catchment area. We have the roof that captures the rain. And then we have a storage volume, which is of course reservoir of the tank. We also have secondary components. We have a conveyance system. The gutters can be understood as a conveyance system. And then also there are treatment considerations, even with rainwater. Now, of course, neither of these secondary components are really going to factor into your calculations for this assignment, but just sort of laying them out there. And I'm really putting this forward because I would like to get to this additional component because I think it's kind of fun and you could potentially factor it into your calculations if you are so bold. This is a first flush device. So what is a first flush device? This is a sort of contraption that you can design into your water catchment system that diverts a first flow of rainwater away from your reservoir. Okay, so why would you want to do that? Okay, so with any roof, you're going to have leaves, dust, dirt, maybe animal droppings that you're just not going to want those in going directly into your water tank. So a first flush device sort of allows a first quantity of water to sort of wash the roof, and you divert that quantity of water away from the tank before then diverting the rest of the rain into the tank. So these systems can sort of vary in complexity, as you may imagine. Some of them sort of remind me of sort of Rube Goldberg contraptions, sort of to automate through sort of basic physics principles to divert that first flush of water away from the tank, but then sort of switch automatically. And there are a variety of examples in this rainwater catchment systems book. which are interesting and kind of fun. So you know, we're all sort of familiar with roofs and tanks, but this is kind of a cool component that you see talked about here and there. And if you are so bold, perhaps you could factor this into your calculations. So what are the calculations that I'm talking about? So I mentioned runoff coefficients. So runoff coefficients are an essential constant that needs to be factored into your equation here. So as you can see, supply equals rainfall times the area times this coefficient. So what is the coefficient? So depending on the material of the roof, the amount of rainfall that will be sort of shedded off the roof can vary. So you can imagine if there is a clay tile roof, a lot of that water might actually sort of seep into the tile itself before being shed off the roof. Another material, evaporation, could be a factor. So you will have to read through the prompt and determine what your coefficient is to factor into your calculations here. Okay, so let's jump into a very brief example that can help us understand or perhaps complexify this calculation a little bit and make it sort of a bit more of a complex challenge here. Okay, so we're going to have two scenarios. In scenario A, we have 70 millimeters of precipitation in 1 month. Scenario B, we have 70 millimeters of precipitation in 1 month. And in this scenario, the two systems for in each scenario, or the single system in each scenario, is sized identically. Which one is more reliable? Now you may be scratching your head. They're both the same system. There's the same amount of rain. What's the catch? Well, the catch is that the precipitation varies over time. Okay, so in scenario A, we're going to go through 1 month where the rainfall events are distributed equally over the course of the month. And in scenario B, there's sort of this major rainfall event at the beginning of the month and then no rainfall in the second half of the month. Okay, so let's just work through our numbers here to help us understand why the variability of these rainfall events can be so critical when designing a rainwater catchment system. So let's start with scenario A here. Each rainfall event in this example is going to be 5 millimeters of rain. Demand, which you are going to have to define yourself in your response. Demand we have here as 0.25 cubic meters per day. And we have 100 meters, 100 square meter catchment area and a sort of basic 2 cubic meter tank that starts off half full. Okay, so let's just run through the days here. Day 1, the users are going to need to consume some water, so there's 0.25 gone, but it also rains. Okay, so we actually have a net gain on this day. Then day 2 on Monday, there's some consumption but no rain. Day 3, Tuesday, more consumption, but it rains. And we cycle through on this sort of sequence here, and you can see that the amount of water in the tank is oscillating roughly within the sort of center of the tank here. That's meaning that all of the water over the course of the month is captured. And I would argue maybe this water tank is maybe a little bit too big, but it is, for all arguments, appropriately sized. Okay. And again, 100% of the water is captured for consumption. Let's move over to scenario B. All right. How is the reliability of this system considered factoring in these this different sort of sequence of rainfall events? Again, all of the same quantities, all of the same sort of water system. All right. Sunday, consume, rain event, consume, rain event, consume, rain event, etc., etc. And you can see here now, the water tank is full. And we continue going at this rate and we consume, but then it's beginning to overflow. Consume, overflow. And we can go through this sequence. And as you can see, the tank is too small. All right. Now, because all of this water has been overflowing, we have not captured all of the water. Okay, so let's keep going. Week 3, we consume, we consume, we consume, we consume, consume. Till we reach week 4, and now we have no more water. Okay, so as you can see, the amount of rainfall between the 2 months is equal. The size of the tanks in this example, they're equal. But one scenario is 100% reliable, and then scenario B presents a condition where the same system is only 79% reliable. Okay, so I hope this example sort of paints a picture to you of how you need to proceed with this assignment. Keep in mind, you are going to be designing a system over the course of the year. Data is presented in months. You may want to extend out to 2 years, up to you. But just a little sort of hint or suggestion, highly recommend developing a kind of spreadsheet for yourself. This will ensure that you're thinking through the details. Okay, so again, these slides are going to be up on CourseWorks for you to review and to get at some of those links that I've shared. And again, visit me for office hours, also posted on CourseWorks, or just send me a message and we can find a time that works for us both. Okay, so thank you so much and good luck. All right.